Without any further ado, I'm excited to introduce Professor Xiaopeng Li. Dr. Li is an associate professor in the Department of Civil and Environmental Engineering at the University of South Florida, USF. And he's also the director of the National Institute for Congestion Reduction, NICR, a US DOT National University Transportation Center. He established the Connected and Automated Transportation Systems Lab that houses two L3 connected automated vehicles. He's the first to hold the Susan A. Bracken Faculty Fellowship at USF and is a recipient of a National Science Foundation Career Award. He's also served as PI or co-PI for a number of federal, like NSF, USDOT, USDOE, local, such as state DOTs, UTCs, and the I-4 corridor program, and industry grants. And he's published around 90 peer-reviewed journal papers. His major research interests include automated vehicle traffic control and connected and interdependent infrastructure systems. So Professor Li, with that, I will let you take it away.
Thank you, John. I really appreciate it. It's my great privilege and honor to have an opportunity to interact with our C2 Smart colleagues and friends. And I also want to thank Dr. Joe Cho for inviting me to this opportunity in the first place. I'm going to mention him later. So today, I'd like to talk about some of my past work and recent thoughts about how we can realize cooperative automated transportation systems. I would like to start with connected automated vehicles. For many of you might know what they are. Connected vehicles are just communications. Vehicles can talk to each other and the infrastructure units. Automated vehicles are just vehicles drive like robots. They control themselves. We, as scholars, have really high hopes on the benefits of connected automated vehicles, or CAVs. Regarding safety, we hope it can reduce over 90% of the crashes at least. In terms of mobility, we hope they can multiply the capacity, such as tripled, even quadrupled. In terms of energy efficiency, we want to have significant improvement, like up to 50%. And what was exciting was that this technology was demonstrated like 20 plus years ago. For example, by PASS Berkeley. With this, it seems like we're on the right track to a utopian world look like this, where all road users of almost can exist in harmony without even any stop. So that's great, but where are we now? We want to have some status check. So current status, if you look into the deployed and implemented technologies at mass scale, you're going to see the automated vehicles are really ahead of the curve, because we've seen many level 1 and level 2 automated vehicles running on the road. Maybe many of you already have automated vehicles with these features. So we can see that almost most new production vehicles have autopilot, adaptive cruise control, this kind of automated vehicle features or AV features. And this penetration rate expects to increase a lot over the years. And I want to draw your attention to the key technology called Advanced Driver Assistance Systems, or ADAS. And the component that is most relevant to transportation system performance is longitudinally would be adaptive cruise control. And many of you may have cars with this capability already. It's just like you have an option to choose the desired headways 1, 2, 3, 4, and then this vehicle is going to automatically follow the preceding vehicle without your input on the gas or the brake. So that's the status of the state of the practice. Well, and we're going to look at the benefit. Safety, it is reported that ADAS vehicles could reduce body injury claims by 27% and reduce property damage claims by 19%. Tesla has a more detailed report about the mileages per crash, and we can see that if you convert that into the collision rate, it improves the safety to as high as 80 to 90%, which is pretty promising. If we compare that with our hope, we're not that far. At least we're on the right track of improving safety with AV technologies alone. What about mobility? You know, it's the fact that these companies don't report the mobility performance of these features. So we have to conduct the field tests ourselves and get the data from other collaborators. So we basically, with this data, we analyze the trajectory data with traffic flow knowledge and convert them into flow and density rate. We plot out these relationships, also known as fundamental diagram for ACC vehicle from automaker 1. And let me see whether I can you see my, let's see, I need to find a pointer, let me see. All right, ACC vehicle 1 and also ACC vehicle automaker 2, and also comparing them with the data we extracted from human-driven vehicles. And we see that on the contrary, the capacities of these ACC vehicles or low-level AVs are comparable to that of the human drivers, or in some settings even lower. So this is quite far away from the target of multiplying capacity. Then energy, we also did some experiments to compare human-driven vehicles and these production AV vehicles' energy performance. So basically, both of them amplifies traffic oscillations and form a stop and go traffic eventually. ACC could, or AV could improve the energy slightly, but that's still not close to the target, and there is still some room, quite some room for improvement. So with this, we can see where the potential benefits of the next phase of connected vehicles integrated with automated vehicles. Let's look at the marginal benefits of connected vehicles on top of automation. So in terms of safety, you know, though we hoped CVs could improve the safety a lot, but now it looks like from the real world, we observed safety benefits from AVs. They're coming, and this is sort of like it reduces the marginal safety benefits of CV. And I think my bold guess is that AVs alone can improve a lot of safety, and CVs can have some marginal improvement as well. But the major potential in the future will be at mobility and energy, because from what you see, AV seems like doesn't improve much on mobility and energy alone. And the best outcomes is like integrating AV and CV, so we can have cooperative driving automation transportation systems, or CDA transportation systems, to realize the full potential of mobility and energy. However, it is not a smooth route down in the road. So we know that FCC provided DSRC, the signature technology for connected vehicles, in 1999, but they took it back in 2020, disappointedly. But the good side is we still see exciting research and piloting programs going on, like an NYC connected vehicle project. That's proud of your city. But overall, compared with AV technologies that are already widely deployed in commercial products, CVs are limited in pilot tests and research projects. We don't have as massive evidence showing CV benefits yet. So why do we have such great challenges? I'm going to talk in more detail. There are many reasons from different sectors, but I'm going to just talk about some visions some challenges that I perceive from the perspective of engineering, from these three perspectives: system, technology, and user incentives. So first, the challenge is system complexity, and let's just look at it, and we hope to address it with system modeling. We know AV technology alone, if you get to the control level, it's actually not that difficult from a transportation engineer's perspective. It's basically essentially, I know perception of AV is immensely difficult, but on top of that, control is just like reactive control of individual vehicles. That's pretty much car falling plus lane changing. That's what you guys and we're looking at on a daily basis. But if you add C on top of AV, then the problem can be a lot more difficult or complex. For example, we have to consider interactions of multiple vehicles, and we want to predictively control their prescriptively control their trajectories in a predictive manner. So, for example, you can want to smooth all these vehicles' trajectory and let them to properly coordinate with the traffic lights to maximize the traffic performance benefits. So we actually have done, we're among the first batch of publications in the methodology work and in this area. And, we proposed a number of models. And, just to give you an example, I'm going to talk in depth of some of our recent work regarding to the key to CAV mobility and energy. So why did I highlight longitudinal control? Because it looks like longitudinal control is the key to realize CAV benefits from mobility and energy. Platooning, you might have heard of this, is using CAV to essentially reduce vehicle gaps. So if we have smaller gap, we're going to have smaller headway. That means higher capacity and less congestion, mobility benefit. Smaller gap, you can even sometimes coupled with electric vehicles. That's the future of automated vehicle technology. Due to the aerodynamic benefits, we're going to have less energy consumption and less emissions. So overall, you can see as vehicle gaps reduce, the benefit increases. So that's why I want to introduce this work about how we can form Platoon. So I'm going to use this example as a sample of the work that we have done in this area. So this is the example of problem. We consider a stream of AVs indexed from 1 through I, from downstream up. We consider AV effective length L, including the Platoon gap. And at the beginning, they're separate. And we know each vehicle's location and speed and other states. And the objective is to platoon them together. So by the final time t, which is also a variable, we want to have them grouped together and cruise at a platoon speed, or common platoon speed, Vd. So this is a problem, and we're going to control the vehicle trajectories, actually plan a vehicle trajectories, more precisely speaking, which is denoted by xi of t. That is location of AVI at any time t during the planning horizon. And we want to plan the trajectories subject to the following constraints. First is kinematic constraints. Each trajectory's speed, which is the first order derivative, is bounded from 0, and the v bar 0 is not backing up. V bar is speed limit. And the acceleration, or the second order of the trajectory, is bounded by a minimum acceleration or maximum deceleration a under bar, and maximum acceleration a bar. In safety, two AVs are spaced, or two CAVs are spaced always no less than the Platon gap L before T. So before the Platon together, we don't want to have them collide. And trajectories will be controlled to optimize some performance measures or objectives that are related to mobility and energy. Upper level optimization, so it has a sort of like two-stage structure. The upper level is to minimize the docking or platooning time T, and the lower level is to has two components. The first component is minimize the sum of squared acceleration, which is to smooth the vehicle trajectories, just to reduce the energy consumption and improve driving comfort. This term is simple and has been used a lot for trajectory control. The second term also corresponds to the mobility. We want to minimize the uncovered distance from free flow. What is that? So suppose that a vehicle, if it is not constrained, it's going to drive at the free flow speed V bar. But after the trajectory control, it may need to slow down and negotiate with other vehicles to form the plateau. So the shaded areas, we call it its uncovered distance. So smaller this area, better the mobility, and better, less the influence to the downstream traffic. So with this, we can build a complex optimization model to approach it. You know, this model is nonlinear. It has infinite amount of variables, has differential equations, and it is for real-time applications. It's not a trivial problem. So that's why they need us, to researchers, to solve complex problems. So how do we really address it in an elegant manner? So I don't want to put it to a solver, which may give you a result, but not that appealing. I want to look into the problem structure and analytical properties and try to find the best way to solve it. With that, we can get some really fast heuristics to construct near optimal solutions to guide the real-time control. And also, I want to look into the exact solution as a benchmark to see how well our heuristic will do. And finally, we will verify it with numerical examples. Let's look at, give you some flavor of analytical properties. We actually started our mindset from a concept in geography called time geography. It basically, so the term is called activity cone. I can illustrate it in this way. Consider there in this space-time diagram, there is a vehicle, and it has a lower speed limit 0 and upper speed limit V bar. So that means this vehicle's activity range can be confined within this time-space cone. We call it activity cone. It's just similar to the relativity theory developed by Einstein. If you know two of these positions, you can shoot two cones and confine the activity of these vehicles within this prism. We call it activity prism. Right, so our contribution is further sort of like a downgrade that macroscopic concept to microscopic vehicle movements. We can add the constraints of the continuation of vehicle speed. Vehicle does not have speed jumps and its accelerations are limited. That's with that, we can see that we came up with this second order cone and second order prism, a lot smoother, and but it works very well to confine the feasible region of vehicle's activity. I mean, this is the very basic concept, but we can sort of like build upon it and make it revised based on the interactions of different vehicles, and finally identify the feasible range, the minimum feasible range for each individual vehicles in the traffic stream. And with that, we can actually solve the upper level problem in that two-stage structure analytically. This is elegant. So this is a nice thing of analytical study. Sometimes if you want to take a step further, you can just, you can save lots of energy and solve this problem. But we do have the lower level problems. So we came up with fast heuristic that is also inspired by the analytical analysis of this cone structure. We just look into the feasible cone and find within the feasible cone, we can easily construct a smooth trajectory for the first vehicle, and then we shift that down and we merge that with the second vehicle's cone and construct the second vehicle's trajectory. And this can be done repeatedly until we find all these vehicles' trajectory. So we can easily populate the planned near optimal vehicle trajectories as a collection of simple piecewise quadratic functions or polynomial functions. That can be done in no time. And you're going to see in the numerical examples. And with this, we can also look into the structure and prove that under certain cases, for if we get the feasible solution, and this is going to be optimal for the squared acceleration objective component. And for more general cases, we look into the general solution. Then this is just like using time expounded networks or time-space networks and analysis to discretize a system. We basically, this is just a simplified representation of this problem. We look into one vehicle, but the essence is find the optimal trajectory or the shortest path in a way, right? So with the feasible cones that we have created, we can overlay the feasible areas to reduce the candidate routes or candidate trajectories largely. Therefore, we can improve the solution efficiency. So let's look at how these customized algorithms and theoretical properties would work. So we first tested the exact algorithm. Okay, so basically we created a number of cases for different problem settings, right? Different initial settings, different constraint parameters, and we tested, we solved them with the exact algorithms. The first, this column here in the box is without the feasible cone reduction, and the second column is with feasible cone reduction. We can see that it's going to reduce the solution time to its almost 1/3 of it on average. So that is great. That says our theory works. It improves the solution efficiency. And then let's look at the heuristic solution here. Look, it can solve the problem within the centiseconds. Actually, this is just some intermediate results. After we further improve it, we can solve it in the milliseconds, which is really great for real-time control. And this is not just some theoretical theoretical problems, but can be implemented in real vehicle. And we also showed why this optimization algorithm is better than like reactive control, because in terms of mobility and energy. So we have published the relevant work. Now, I just gave you an example about how we do the in-depth work. Now we take back and look into the breadth of the problem. We only checked on the sort of like a simple setting, one lane pure automated vehicles, pure CAVs. But in real life, we're going to probably have a mixed traffic for an extensive period of time, including both human-driven vehicles, HVs, and CAVs. And they may have complex lane changes, as these trajectories show in this space-time diagrams. We've done some modeling analysis here, and published some papers. And from these studies, we realized that one key to successfully control CAVs in mixed traffic is to predict human-driven vehicle trajectories or their behaviors precisely or in a good accuracy. Because, this is simple, because we want to know how other vehicles will drive in order to design our own trajectory. In this way, we can improve the system performance. If we don't know how other vehicles would drive, the subjective CAV control will be very conservative. We're not going to be able to harness the benefits related to mobility and energy. So in order to do this, we need to have data to understand. But whether you believe it or not, we don't have many trajectory data for us to play with. The one well-known set would be NGSIM, but that's 15 years old. So we actually conducted the study to collect our own data using drone, helicopters, advanced video analytics. We developed the customized tools and extracted arguably the longest trajectory, about 1.2 miles long, including a comprehensive cycle of bottleneck development and dissipation. I'm talking about the comprehensive trajectories, including all vehicles on this road segment. So the data is publicly available here. If you want to look into it, please feel free to download it in this GitHub webpage. And with the data, basically, before we control the automated vehicles, we are actually, we need to predict the vehicles' trajectories around. They might be human-driven vehicles. So essentially, a core problem is using history trajectories to predict immediate future trajectories. This is a simple illustration. On one lane, the trajectories of the few vehicles. Blue ones are downstream human-driven vehicles, and the red ones of the controlled CAV. We're going to need to predict the immediate downstream trajectories as these dashed lines illustrate, and then we can control this red trajectory properly. So we've done lots of work into this recently, trying physics methods using physics models and pure data-driven methods such as LSTM neural network, and combining physics and LSTM. And we found that looks like combining physics and the machine learning would be a good way to go, because that gives you the best performance in terms of position and velocity accuracy. And recently, we're looking into this idea of safety-aware predictions and control. So when we predict the vehicle trajectories, we want to consider the follow-up like CAV control. We want to make our predictions on more of the safety side, but we don't want to be too conservative. We still want to maintain the mobility. So how to balance the guarantee of safety and the mobility need is an interesting problem, and we're trying to integrate in physics and machine learning to do this work. So hope that will give you some samplers about how we approach the solutions to system complexity. And of course, that's not the comprehensive story. There are many other things that need to be looked at, and I would invite you to look into this space. after we have all these complex models addressed, we don't want to stop at models in our papers. We want to realize them in technologies. We want to convert them into technology innovation. So I'm going to talk about the second aspect in our roadmap, next step. So actually, in lots of models, we take it for granted that all these vehicles can be perfectly controlled and their trajectories can be controlled precisely, which is key to the success of CAV operations, but it is not as easy as it sounds. You know, we did some experiment with the state-of-art vehicles, production AVs, you know, and also we customized them as well using state-of-art control algorithms. It is not easy to ask a vehicle to exactly follow a prescribed speed profile. You see, at different runs, they have different errors, just with the existing methods. So with this kind of control, I mean, this vision of a cooperative automated transportation system is impossible because when vehicles plateau together, they will have high risks of colliding into each other. So actually, I want to emphasize here that it is important for us as civil engineers, as transportation engineers, to participate in this movement of technology innovation. We need to create new technologies to realize the vision of cooperative driving, not just a passive waiting to observe or evaluate technologies developed by people from other fields. I'm going to explain more reasons why it has to be us. But right now, we want to create new technologies ourselves. So how do we do that? So we start from something small. We created reduced scale AV test beds using like a Raspberry Pi small vehicles, and we add the speed and location following algorithms, and we developed the precise trajectory control by combining model predictive control and reinforcement learning. We're still working on it. It's not as simple as it looks like. So we try to really control these vehicle trajectories a lot better than the state-of-the-art production vehicles. And after that, we're going to move this results to our full-scale CAVs. You know, this is something we're really proud of as a civil engineering lab. We're probably one of the unique group that assembled the vehicles ourselves rather than purchase the vehicles from a vendor. We developed the drive-by-wire control. We assembled those multi-source sensors, and we developed our platform and integrated it with the US DOT Karma platform. And of course, with this platform, it's something to brag when important people to visit us, right? When important people visit us, like legislators, government officials. But more importantly, it is supporting our research. So, for example, the previous section about problem modeling is system modeling is all talking about trajectory control in paper, but now we realized in real life. This is an example. It is coordinating a CAV's trajectory with a signalized intersection in mixed traffic. If you look at the video in the on the top, the highlighted red box, it pinpoints the CAV, and the other vehicles are running it are HV. So at the beginning, the HVs in the downstream will just drive at full speed to the signal light in the downstream without realizing that it is still red. But this CAV, after communicating with the signal the roadside unit at the signal light, it was designed its optimal trajectory to smoothly glide through the intersection. You're going to see that the effect is like this. So it's going to slow down and not immediately follow them, but these downstream vehicles will be forced to stop, but this one does not need to stop and smoothly glides through. All right, here is another example down here. And this is just one downstream vehicles. You can see this downstream vehicles will make a stop, but this upstream vehicle does not need to. Remember, this is a mixed traffic. So, and also we have done some experiments on lateral vehicle control, and we also use it to calibrate microscopic simulations and help HWA provide guidance and suggestions about how to simulate CAV. And these results or tests are still preliminary, and I can say that all the very bottom level trajectory control still needs to have a lot of improvement to realize the full potential. We're still looking into the very basic trajectory control, incorporating MPC and the database learning, reinforcement learning. And we hope to report some exciting results in near future. That is the microscopic end, but we also, as system engineers, want to consider the whole transportation systems. So on the other hand, we're thinking of proposing edge computing cooperative control framework that combines cloud, edge nodes, and individual edge devices. These are, cloud is TMC, edge nodes are just like roadside units, traffic lights, and edge devices would be different vehicles, road users. Right, this is consistent with the FHWA Karma ecosystem. It has Karma Cloud, Karma Streets, and Karma Messengers and platforms for vehicles. So we actually are helping them to develop the core and algorithms for their first batch of use cases, like intersection control, and we incorporated the newly issued SAE J3216 standards on cooperative driving automation, different classes. And we're not only doing this simulation, but we're doing the field tests. We're right now integrating their development to our lab vehicles and try to conduct some first stage integration tests at the end of November. Another thing I want to mention is that we really don't want to be satisfied with the technologies that they told us. We want to think further, see whether we can drive all the way to the extreme of the technologies that we want. I mentioned that before, the system benefits increases as the vehicle gap reduces. Let's push it to the extreme. That becomes zero gap, right? If that is zero gap, then vehicles are going to physically connect together. And this is consistent with a recent concept called automated modular vehicles. So these kind of autonomous pods can dock and undock when they're driving, right? It has lots of advantages, like allowing on-route transfer, allowing different on-route charging operations and different package delivery services. And also, this concept has been adopted by like Chinese railroad operators to accommodate the varying passenger demand. And I want to note that Dr. Cho is a pioneer in this research area, and he's probably one of the first looking into the system operation problems, and I'm fortunate to collaborate with him on an NSF project right now. And we're working on more of the relatively microscopic problems like shuttle system, corridor system, this kind of fleet modeling and fleet operations. We have some publications, but we're not satisfied with that. We really want to implement it with physical tests. Right now, we're working on the reduced scale cars, and once it is mature, we're gonna move it to our vehicles, full-scale vehicles, and eventually, hopefully, that'll be on tracks, because tracks, the benefit is the most articulated. All right, so now let's look into, once we have the innovative technologies, how do we have the users buy into them, right? How do we incentivize users to use that technology? So do we have a model to incrementally implement these technologies while giving all the players sufficient benefits? So let's look at how we do that. I'm gonna bring you to a point that I made earlier. It is important for us not only evaluating technologies, but also to create new technologies. Why? Because if you don't do this kind of things, people from other sectors may not have incentive to do. We may have lots of enthusiasm in the automated vehicle space alone, because the AV benefits like driving comfort, safety, can be directly applied to the subject, AV driver and rider, which can be directly converted into commercial profit, right? They can sell products at a higher price and customers will buy into it. But the marginal benefit of CV on top of AV is not that intuitive. The cost is direct. The vehicle needs to absorb the cost because it involves added equipment. But the benefits is not necessarily always on the subject vehicle. It's mostly going to other vehicles, because if you're cooperating, you disseminate the information to other vehicles. The primary beneficiary would be the vehicles surrounding you, right? And also to have these benefits prevail, you can only have that realized at relatively high market penetration rates. And that may take quite a while. So existing lead technology players, AV companies, TNCs, they don't care much the marginal system benefits, right? They care more of their own in vehicle fleet's performance rather than that marginal benefits to system congestion. And they do not want to invest on a system with low penetration because they don't see much CAV benefits. So it's important for us to create new technologies ourselves to address these voids, because we care the transportation systems and we'll work on the infrastructures, and we strive for social benefit as a whole. Right, I'm going to talk about some examples of technologies and mechanisms we're thinking to address this aspect. First is to reduce the initial cost of a CV, so make the adoption of CV not that expensive. This work is inspired by animals communicating with colors. For example, some sea creatures, they can change the colors on their body to convey the message. So we see actually there's lots of lighting sources and receivers in transportation systems. They're readily available. We don't need to have additional infrastructure investment. For example, this is one on the information transmitter side. This is one picture I took in one night when I was at the Walmart parking lot. I saw a vehicle flashing a rainbow-like running light. It looks like we can have lots of information inside of it rather than the cosmetic purpose. And also on the roadside, we have lots of this kind of dynamics panels like variable speed messages. And we could sort of program it in a way that can be read by autonomous vehicles. And in terms of receivers on the vehicle end, newly produced vehicles, most of them have equipped with cameras all around the vehicles. And also on the roadside, CCTVs, right? Surveillance cameras are widely available. We could take advantage of them. So we got a project from DOE, so-called Visual Enhanced Cooperative Traffic Operations Systems Vector. We're trying to develop a protocol of using flashing light and arrays to communicate the information. And we also build upon it. We want to distribute to the cooperative driving automation control with this kind of communication scheme. And also, in order to, once the infrastructure is ready, once the connected vehicle hardware is there, how do you incentivize people to use it and cooperate and generate the system benefits? We know that system benefits do not necessarily mean every individual is benefited. So we need to have a mechanism to convert the system benefits, at least partially, to individual benefits. So each individual is willing to make sacrifice. Otherwise, if they're just doing some things that sacrifices themselves but benefiting others, the system's not going to hold, right? So we could think about tradable credit systems or other mechanisms using blockchain digital currency, piggybacked with autonomous vehicle computers, right? Autonomous vehicles often have powerful computers, and you can have them as smart agents to handle some kind of currency credits and have them communicate and have this kind of credit trade while they're cooperating. So this is a brand new research area, and lots of prosperous opportunities for algorithms development, system design, and technology development. So in the end, I would like to acknowledge the major collaborators. And I have worked with the colleagues and students. And also I want to acknowledge all these sponsors. So, and I hope they can continuously support us to realize the vision of cooperative transportation system, cooperative automated transportation systems. Our lab is named under that spirit, CATS, right? Connected Autonomous Transportation System. And again, I hope that we could integrate our modeling expertise with technology development to be active players to push forward the technologies, not to wait till only the automakers, only these IT people working on this space, so as to realize the systematic benefits. With that, I'm going to conclude my speech, and I want to note that the first time I visited New York, and someone told me that the Empire Building was made special with this special violet light 1 day or a year or something, just to celebrate the success of the NYU students. So with that, I want to bring my earnest and warmest wishes to you guys.
Professor Lee, thank you very much. That's actually our commencement day every year when the Empire State Building is turned purple for our students. So that was a really very interesting and thorough approach to the roadmap to CAT adoption. I'd like to open, as Professor Lee said, open this time for Q&A for our audience. I see we have one attendee has raised their hand. I will call on you in just one moment, and I'd like to first present a question that we have, which is, how does this research inquiry address the possibility that future human-driven vehicle trajectory will change in response to CAV trained on historical human-driven vehicle trajectory data, so that we have very unusual data set that erupts from this training the CAV on historical data?
So how to, can you read it again? I'm sorry. I'm just
sure. So it's, how does your research address the possibility that future human-driven vehicle trajectory will change in response to CAV that have been trained on human historical data? So the past data not predicting the future human behavior.
Yeah, I think I might have, I saved some backup slides right for this question. I knew you would ask me about that question. So we did some experiments about how human-driven vehicles would react differently to autonomous vehicles. right? If they reacted the same way, we can use comfortably use the history human-driven vehicle data. Right? If they react differently, maybe we need to do some new experiments. So we basically try to experiment two types of autonomous vehicles. One is with conspicuous settings. You can see it and understand it's an autonomous vehicle. The other is you don't tell it is an autonomous vehicle or not from the appearance. So we've done lots of analysis, but the conclusions are like HV behavior models might be different in mixed traffic compared with existing traffic. For conspicuous settings, that is when you can recognize the surrounding vehicles are automated vehicles, you may react differently. But for conspicuous AVs, existing HV behavior models in pure AV traffic still apply to mixed traffic. There is no statistic difference between their car following behaviors and the macroscopic headway settings. So basically not too much difference in both macroscopic traffic flow characteristics and a microscopic car following model. So in that way, we can at least get a lot from the existing data. That's one perspective. Another is actually, when you drive, you only look at the downstream vehicles. If you're automated vehicles, your downstream vehicles may not react too much on you. So if you can, in that way, that's why we look into this one lane setting and use the downstream to predict its trajectories. But I mean, of course, it's an open research question. We need to collect more data and conduct more experiments to have this addressed.
Sure. So I'm going to turn it over to, forgive me if I'm mispronouncing your name, Liana. I'm going to allow you to unmute and ask Professor Lee your question directly. Liana, are you there? Okay. In the meantime, then, we have a question from Hella, one of our students. How are the CAVs distinguished from human vehicles in the simulations that you showed?
Yeah, in simulations I showed, it's like we used automated vehicle trajectories we collected, or CAV trajectory we collected to train the car following and then lane changing models, and we put that into the simulator. Of course, that is just to show the framework, but really how it is different, it really depends on the programmers of the automated vehicles. If they tell you the source code, you will know the difference. If they don't, you have to collect the data to do some reverse engineering to understand their behavior. So that's what all we do, right? We've done that a lot to calibrate the human driver behaviors, like car follow model, lane change model. You can do the same thing for the technologies of your interest.
I have another question. So your roadmap focuses on introducing CAT in mixed traffic scenarios. What do you think of intermediate introductory measures such as dedicated CAV lanes as a way to lead to deeper market penetration?
Yes, yeah, we actually have done some work there, and not sure if I can, yeah, like this one. Yeah, this is this leads to some kind of land management. It's like I probably don't have the slide. So basically, it's basically the managed lanes are like extreme of plateau vehicles, platooning the vehicles and on the same lane, So that is yeah, that is only possible if we can solve the technology issues, as I mentioned. Otherwise, we can see all these demonstrations, but we don't see the reliable operations of these. And even if they're in the real world, if we don't actively work on it, so that really the headways of platooning, and also the marginal impacts. So it could be more directed towards the individual users rather than the system benefits.
One interesting aspect of your presentation is the way you're posing these interdisciplinary questions, such as about user adoption and the right incentives for wide CAV adoption. what other areas do you think the field would benefit from with additional focus from transportation engineers?
Yeah, that's a great question. Actually, you see, this topic is almost linking all areas of engineering and many other areas in social science, economy, right? So, I mean, to address all these problems in a comprehensive way requires collaborations of researchers across different domains. And also, as civil engineers, we want to get out of our comfort zones to try to understand other disciplines. Because my experience of interdisciplinary collaborations, it will be only, it can be one way of success is to have everyone somehow understand others' domain, and or at least a group of people who could serve as a connector to understand other domains to a certain degree, to have these problems well addressed in a really interdisciplinary manner, rather than each one works on their own problem. Regarding the problems, there are many other problems. People are talking about even ethics, right? Insurance, all these things, but I cannot enumerate them, but there are lots of interdisciplinary problems of interest.
Okay, we have time for one last semi-related question. I like to ask esteemed researchers sometimes. You mentioned the importance of creating new technologies. So I was wondering what specific problems should our students work on to create these new technologies, such as those that are key to precise trajectory control?
Yeah, just to think about what has happened. Like I said, connected vehicles started in 1990s. It was 10 years before Google car development. But right now, automated vehicles are running, but why connected vehicles are not deployed? Think about it. And then, if you have this kind of questions, and then you'll know where the problems are, and then you can consequentially find the right tools and knowledge to solve the problems. And also for civil engineering students and transportation engineering students, I would encourage you guys to take interdisciplinary courses. I took, in my graduate studies for 9 semesters, I took at least 3 courses a semester in all different areas like math department, computer science, electrical engineer, industrial engineer. So they are quite beneficial. And if you have time, I would encourage you guys to look into this relevant areas, at least in the future. If you get to talk to the people who know the technology, you would not feel strange.
Professor Li, thank you very much. This is very interesting. And if it's all right with you, we can send some papers out to the audience that you've written recently that are relevant on this topic. There was a question earlier asking for that information. So some very quick ending notes. If you enjoyed this webinar, definitely follow the C2 Smart Center on Twitter and LinkedIn. And I encourage you to reach out to our presenter to learn more about his research. Professor Xiaopeng Li, USF, and Director of National Institute of Congestion Reduction.
Sure. Likewise, if you want, you can send me that your message once it's published. We can either tag it or forward it in our UTC webpage.
Absolutely. Thank you very much for joining us.
Thank you so much. Thank you, Joe.